Assalamualaikum and a very good morning, everyone. First of all, I would like to thank all of you for participating in this public talk. Allow me to introduce myself. My name is Nurul Husna binti Hasmi, and I am your moderator for today's event. We are very honored to have Associate Professor Dr. Boyang Albert Lee with us today. And before we start, I'll make a brief introduction to our speaker. Associate Professor Dr. Boyang Albert Lee earned his PhD in Computer Science from Georgia Institute of Technology, USA, and his expertise is in learning knowledge to support domain-independent narrative intelligence. And today's topic is multimodal AI in the era of gigantic pre-trained models. What's next? Doctor, as of now, we have Tesla who uses AI in their cars and ChatGPT, a chatbot developed with AI technology. Personally, I'm not from IT field, so I am curious on how AI have developed and how much more it will develop in the future. So without further ado, I would like to welcome Associate Professor Dr. Boyang Albert Lee to give his talk on this topic. Please welcome, Doctor.
I am still. Hey, thank you very much for the introduction. I'm very happy and glad to have this opportunity to speak to audience at University of Malaya. And let me share my screen. So wonder if there is a way for me to sort of interact with our students in any way. But let me share that. Okay, so I am looking at my slides now, so I wouldn't be able to see you. But if you have anything, please leave that in the comment, or I'm sure the host can give you the opportunity to speak maybe a little later. But in any case, we're going to talk about, multimodal learning. I'm going to talk about the gigantic pre-trained models, right? So I'm pretty sure many of you have heard about ChatGPT or probably played with ChatGPT. If you haven't, I strongly encourage you to. It is really a transformational technology. But in case you are just not too familiar with the history of this development, I want to give you some background first, right? So the technological trend kind of started back in 2018, right? So when we had those two models, Elmo and BERT, and those two models really showed us that scaling up, increasing the number of parameters in the neural networks and increasing their training data is an effective and reliable way for us to increase model performance. And since then, we see a exponential increase in the model size, right? So you see this is a straight line, but this is actually on a log scale. So this is straight line is denoting is exponential growth. And in 2020, something really happened, right? GPT-3, you can see that it sits significantly above the straight line, which means it has achieved super exponential growth, and which is really something amazing by itself. So you probably have seen ChatGPT and its list of tremendous achievement. And to me, from an AI perspective, there are really two things that ChatGPT is very good at and has pushed to new heights, right? So the first one is that it can reliably perform open domain conversations. All the previous chatbots, you probably have used things like Amazon Alexa or Apple Siri, or there are a bunch of chatbots from Chinese companies as well. So they can perform conversation in a few predefined narrow domains. For example, they can maybe find you a song, or they can set you an alarm clock in the morning. But those are limited tasks that are predefined by humans, and they're restricted to these tasks. Whereas ChatGPT can really talk about anything you wanted to talk about, and is actually really good at it, right? So that's something that is exceptional and we didn't have before. A second one is it can follow a huge variety of human instructions. You could ask it to, write you an essay based on any topic. Things like business. People have been, business management professors have been using this to answer questions, and it's doing a pretty good job. But and then there's GPT-4 that just came out maybe a month ago, and it's pushing things really to the new height. So I guess traditional benchmarks of artificial intelligence are no longer sufficient. So they are testing this model on a lot of human tests. The tests are designed for humans. And here you see, SAT or GRE or AP test. AP is kind of a test that is popular in American high school, which is really kind of moving some of the college courses to high school. So those are not easy courses. And GPT-4 is actually doing very well, especially on the subjects that require mostly some degree of memorization, such as history or government or civics classes or psychology or history or things like that. So how do they do it, right? So we don't really know how really ChatGPT or GPT-4 work because they are closed sourced and a lot of details has not been disclosed. But we know we understand how their predecessors work, and I think most people believe that they are just natural extensions of their predecessors. So I want to talk to you about what was happening before, like GPT-3 or GPT-1, 2, 3, and Instruct GPT. So I think GPT-1, 2, 3 follow roughly kind of the same training paradigm. It's actually something really straightforward, right? So the idea is that you can take any chunk of natural text and it will leave out the last word, but you will feed to the model every word, here before the last word. So that's your input to the neural network. And the network is trained to predict the last word. Okay, so here the answer is the word model. And you can use a sliding window, right? So you can use any text. So after you predict this word, you can use every word you've seen to predict the next word, and it keeps going. And it's a very simple way to train this model, and it allows us to use basically any natural text without a lot of human intervention to train these models. So it allows us to really scale training data to a huge amount. And interestingly, if you can scale up the model parameters, you can scale up the training data, even though the training objective is so simple, somehow miracles happen. All right, so with GPT-3, they scaled this to 175 billion parameters, and that causes some capabilities to emerge without necessarily being foreseen by the designers. One of them is known as in-context learning. And a long story short, in-context learning is the ability to follow human instructions and with the help of a few demonstrative examples to perform a task that this model has not been trained on. For example, here we see translate English to French, and the model hasn't been specifically trained on this, but it just trained on like a few hundreds of billions of natural text tokens, and then this ability kind of emerged. And you can see we are providing a few examples about this translation, and we're leveraging on the model's capability to predict the next word given the context, right? So it's as long as you can predict the next word correctly, you're basically identifying the right translation for the word cheese, right? So that's the first capability. Now the second one is so-called chain of thought prompting. So here's one simple math question I'm sure every one of you can do, but the model kind of fails to do without any external intervention, right? So it says the cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have now? And the model says it's 27, right? So without doing anything, the model get it wrong. But the idea of chain of thought prompting is to give you one example of a arithmetic question, and in the example answer, I want to very explicitly state step by step the reasoning process. Okay, so first, if you look at this, Roger has 5 balls. He buys 2 more cans of balls. Each one has 3 in them. So you would say, okay, starting at the beginning, there are 5, and 2 cans of 3 balls is 6 balls in total. So you add them together, it's 11. Therefore, the answer is 11. And when you do that, the model learns to imitate this format. So it can then output a number of reasoning steps. So, and with that, the model can get the answer right. So this is known as chain of thought prompting. And if that is not surprising enough, we have this phrase. So people have discovered, so previously in chain of thought prompting, we had to manually give you one example that contains the reasoning process. It turns out if you use this magic phrase, let's think step by step, then the model automatically gives you that reasoning process without the example, right? So that's something that's really amazing. What we have seen, I think, is that new capabilities emerge from these models when you scale them up to a large number of parameters and a large amount of training data. So in condensed matter physics, people talk about more is different. And for large language models, more is definitely different, though we may not know exactly why that's the case at this moment. So Instruct GPT, which is a precursor of ChatGPT and GPT-4, really tries to push the ability to follow human instructions to the next stage, right? So they realize these models can follow instructions, but not doing so very well. So they design a number of steps to further increase this ability. The first step is known as instruction tuning, which is that they collected a lot of different tasks. Each one comes with some kind of human instructions about how to do the task, and they have human design answers, and they train the model to do those things, right? So the idea is that when you train on one task, you can do that single task. When you train the model on 5 tasks, it can do the 5 tasks. But when you scale the number of tasks up to 100 tasks to 500 tasks, the model learns the generic capability to follow human instructions and to solve tasks that it had never seen before. So that's first step. All right. The second step is that they wanted to give more detailed feedback when the model generates a number of possible answers. They want to tell the model this answer is better than the other answer. So the first step is using a human to do this kind of annotation. So when the model produces 4 answers, A, B, C, D, the human comes in and says, I have a ranking. I think D is better than C, which is better than B, which is better than A, and A is comparable to B. So, and after that, train neural network to learn that human preference. And after that, we have this RM or reward model, and we use that to train the model over a lot of tasks using reinforcement learning. Right? So if you are not familiar with reinforcement learning, it is basically kind of a trial and error mechanism from a huge number of output. The model get feedback consistently, and it kind of learns the best way to maximize the reward. Okay, so if that's kind of a very high level of reinforcement learning. But with those procedures, they really manage to increase the model's capability to follow instructions. And on top of that, we have ChatGPT. And on top of that, we have GPT-4. But are these models perfect? They look amazing. Some people feel that this is really AI or artificial general intelligence. Probably they're not there just yet, right? They're not human level just yet. And there are a few drawbacks, such as they don't really have very good reasoning capabilities. Like for those arithmetic questions, you have to design some prompts manually to kind of induce their ability to reason. And there are more complicated reasoning tasks that you cannot necessarily induce using one or two magic phrases. There are things like hallucination, which is, if you ask ChatGPT to give you a list of papers on a particular topic, it can produce realistic looking paper titles, but if you search for those titles in Google, those are not real papers. Those papers don't exist. And sometimes it can become very gullible. It can believe in anything you say, even though that's appears to be rather ridiculous. Or it can refuse to accept some obvious facts you want to feed to the model. So whether it's very difficult to strike the balance between how much agreement do you want to have with the human. So with those things, there are also other challenges the size of these models kind of impose. And we're going to talk about two challenges mainly today. One is because the model is so big, it's very difficult to train them. Or you can use a supercomputer to train them, but that's very expensive. It's also difficult to deploy these models in the cloud, and where you would receive like millions and billions of user requests. Because the models are too big, and running one request requires a huge amount of compute. So we're trying to see if we can kind of tackle those new challenges a little bit with my own research. Okay, so what I'm let me quickly make sure I don't miss any messages in here. Okay, I don't have anything. Okay, so the first thing I want to talk about is if we can acquire new capabilities, especially multimodal capabilities, without fine-tuning the large models, right? So we've talked about the GPT model's capability to do new tasks, basically acquire new capabilities from some human instructions. But what if the new capability requires the processing of visual information, right? So previously, everything is in text, but what if you need visual information? So one task we are interested in here is visual question answering. The idea is that I can give you an image and I'll give you a question in text, and you have to answer that question in text as well. So given this image, I will say, what is the animal? And you have to answer bird or something like that. And this is kind of a really rich task. It involves a lot of visual capabilities, such as object detection, understanding what objects they are and where they are, and what attributes do they have. Is the animal sleeping? Recognizing the action of that's happening here, and do some common sense reasoning, such as why are the men jumping, and things like that. So we want to solve the task without training the large language models. This is in contrary to conventional wisdom that suggests if you want to use those models well, you have to do some kind of end-to-end training. Otherwise, performance will not be very good. So our contribution is that we show the possibility that you don't need to perform any training, and you can perform VQA pretty well. And our no end-to-end training model outperform Google DeepMind's model called Flamingo on zero-shot VQA V2 with far fewer parameters. So I'm using a few pre-trained models. There are, some of them have been introduced to vision and language data. So from the belief model, I'm using two modules. One is called the image question matching module. So this, what this network does is that you can give me an image and a text, and the model tells you whether the text is a good description of the image. Okay, so they want to classify an image caption pair as matching or not matching. So for the image captioning model, the purpose is to, given an image, describe the content of the image in text. And we also have unified QA. This is a completely text model that is not aware of any visual information, but it has been trained to perform QA on textual data. Okay, so here's basically what the system looks like. So we're taking a few steps. The first step is that given the image and the question, we feed them to the image question matching module, and we use a model interpretability technique. So long story short, what I'm asking the model to do is, assuming this question and the image are matching, what are the image patches? I can divide the image into multiple patches. What are the image patches that correspond to this text, right? So I'm able to highlight some image patches here that corresponds to that textual question. And after that, so that's my first step. And after that, I will feed the relevant image patches to the image captioning module. And the captioning model is able to describe these patches that are relevant to my question. Now, I understand that images contain a lot of information, right? A picture is worth 1,000 words. So if I generate a single caption, I'm not sure if the caption will capture all the information in the image. Therefore, I want to create a diverse set of captions that describe different aspects of my image patches. So what I do that is to introduce some randomness into the captioning model. I'm not going into the details here. So the next step is, after I have the questions and the captions, I feed both into the textual only question answer module. And because both input are in text, the model hopefully can give you the right answer. Okay, so let me give you some example. The question is, what utensil is this? And you can see the interpretability module is more or less capable of identifying the relevant portion of this image, which is the utensils, and the captions are more or less good descriptions of these things, even though they may not be perfectly grammatical, right? So because the captions contain that information, the textual module is able to pick it up, even though the grammar is not always there. So how are we doing in terms of accuracy? So our models are showing at the bottom, and this is DeepMind Flamingo that has more than 80 billion parameters, and those are end-to-end trained. And they achieved on the VQA V2, which is a very popular VQA benchmark, they achieved about 56, and we are 8.5% higher than that without any training, right? So which is, I think, a rather big achievement. Cognitive science, so this is a bit of a speculation from my end, and cognitive science have studied the human cognitive system and the human mind and the human brain, and their conclusion is that there are some modular components in our mind. especially the perceptual modules, such as the one that is responsible for vision, the one responsible for hearing. Those are very modular systems. However, the artificial intelligence practice to this point has mostly been focused on end-to-end models. There's some recent work on modular systems, but they're not very popular. So why is there such an obvious contradiction? So the one hypothesis I'm thinking about right now is that a modular system only makes sense if you have very large models, very large networks. And for the number one reason is that it becomes really hard to fine-tune these models end to end. The second reason is, as the models get large enough, they begin to speak the same language. In this particular case, we use interpretability as a language, and we use human natural language as another language, a communication medium, using which different networks can talk to each other. Right? So with those things, modularity makes sense. So maybe modularity is only useful when you have gigantically sized models. So some of you may have noticed that I have skipped something. I have promised you that I will use large language models to do QA, but I've used actually a textual model that is specialized on question answering. So what happens if we want to switch that to a generic large language model, right? So it turns out we can do that too, but we need to demonstrate the QA task to the LLMs because they have never been trained on QA. So our approach is to generate a bunch of synthetic question-answer pairs from these captions that serve two purposes. Number one, they illustrate the task of QA, and the second, they kind of also describe what's happening in the picture. So they help the model understand the picture as well. And with that, we're also able to achieve pretty good performance, still above the Flamingo level, even though like we still fall short of the specialized textual QA model, which the special training is useful. But the flip side is that we are able to easily switch out the LLM to a large variety of different LLMs. Like some are smaller, some are bigger, but regardless, we are always achieving very good performance. And as the LLMs improve, we can easily gain benefits by switching out the LLM to a newer version. Okay, so that's really the first part. The second part I want to talk about is the second challenge: if we can simplify the deployment of large models. All right, one thing we have seen that people have been designing the prompts to these large models manually, which is known as prompt design or prompt engineering. We know that people have been fine-tuning these models end to end. But there's a third way, which is kind of a compromise, is that you can take the prompt and treat them as basically model parameters. So then you can train them using like stochastic gradient descent. Okay, so you can just train these parameters, train the prompt, just like you train any parameters of the neural network. But this approach, called prompt tuning, offers unique advantages in deployment, right? So imagine you use model tuning, which is to train all the parameters in those models, and you have three downstream tasks, A, B, and C. And once you train the model on task A, you have one specialized model for task A. And so if you have three tasks, you have three specialized models, and you have to deploy all three on the cloud because you don't know how many requests will there be for each model. You have to do load balancing, and there's a bunch of issues that come with hosting three very large models. Now, with prompt tuning, things get simplified because you can fix this model without training that model. You can basically append the prompt you just learned in front of the actual input, and feed everything to the same model. So that greatly simplifies deployment. Okay? But the problem is that prompt tuning requires a large number of training examples. So how can we improve the sample efficiency of prompt tuning? That is, how can we train the prompt using no data or even a little data or even no data? Okay, so the idea we have is called transfer learning. The idea of transfer learning is that, for example, if you want to work with movie reviews, but you don't have a lot of data for movie reviews, what you can do is you can take some hotel review and restaurant review data and hopefully borrow from that to train the model first on domains such as restaurant and hotels that have abundant data, and then take whatever you trained and apply on this new domain, which is movie reviews. And you can, if you have a little data, you can fine tune on the data. Otherwise, you can do zero shot. So our technique, our proposal is that you can use unlabeled domain data from the target domain, from movie reviews, but those don't have human labels. And you can, while you train the prompt, you have to consider the labeled source domain data and the unlabeled target domain data, and then you can do some fine tuning. You can train the prompt in that way, and after that, you get the prompt. You can, if you have still some labeled data on the source domain, you can fine tune on those. Otherwise, you could do things in a zero-shot manner. Okay, so I want to talk about things quickly. I think there's a bunch of technical stuff. I don't want to, go into too much, but maybe I want to give you some high-level intuition, right? So intuition number one. All right. So there is the target domain, but target domain data don't have many labels or maybe no labels at all. So it becomes really easy to overfit the source domain. And in order to kind of generalize the prompt we learn to the target domain, we want to apply some regularization. In particular, we want to apply a smooth decision boundary so that would improve generalization. So here's one intuitive example. Now here we have class 0 and class 1. So those are the two classes your machine learning algorithm is trying to separate. And you can create two decision boundaries. One is the straight line, that is the solid straight line. The other is the dashed line here. So this line here is non-smooth. It's a zigzag line. This line is a smooth decision boundary. And you can see that the smooth line is supposed to generalize better, right? This is sort of an intuitively good decision boundary if you ask a human, right? But there are many cases the machine learning will actually learn the zigzag line. And the problem with the zigzag line is that they're very close to the existing data points. So if this square moves a little bit because of the domain differences, target domain is a little different from the source domain. If the data point moves a little bit, your generalization will not be very good. So we wanted to learn this solid decision boundary, and that's how we apply the regularization. So I wouldn't go into too much detail. I just want to give you the high-level intuition. The second intuition is that we really only care about how smooth the decision boundary is when the target domain and source domains are similar. Okay, so we can look at this part of the diagram. We have two domains, the blue and the orange. And here, the source domain and target domain data are very similar. And this is a scenario where the smooth solid line decision boundary works way better than the zigzag line, right? So, the solid line kind of correctly classifies all the source domain and the target domain data points, where the zigzag line classifies the source domain correctly, but the target domain incorrectly. However, if your source domain and target domains are very, very different in the second scenario, then even if you have a smooth decision boundary, it's not going to help you very much. Right? So in this case, the solid and the dashed lines both have the same accuracy, which is actually poor. So we only care about the smoothness of the decision boundary when the target domain and the source domain are similar. So that's something we managed to incorporate into our algorithm. But I probably don't want to bore you too much with the algorithm details. So I wanted to go straight to the results. So we have a number of domains. For example, the QQP and the IMRPC datasets are natural language texts that are about detecting paraphrases. Right? So given two sentences, you want to detect if they are paraphrases of one another. We have mainly, singly, SIC, and CB. Those are data sets about entailment, which means given two sentences, you want to determine if one sentence entails the other, or maybe one sentence contradicts the other, or maybe one sentence has nothing to do with the other. Right? So those are three classification problems. We have introduced a bunch of transfer learning scenarios, and we have looked at what if you just don't do any transfer learning and just use target domain data to train the network and see if things would improve. So we not only beat the simplistic scenarios where you do don't do any transfer learning, but we also have a bunch of baselines that are very sophisticated, state-of-the-art transfer learning baselines for prompt tuning. And we managed to beat all of these, right? So one thing that's a little interesting is that sometimes doing prompt tuning can give you very high variance, and sometimes it's even worse mainly, for example, if you do prompt tuning, it's actually worse than if you don't do any tuning at all, right? Showing that prompt tuning is very sensitive to the amount of training data. And here, for example, on CB, very high variance and lower performance than if you don't train anything. But with transfer learning and with our way of transfer learning specifically, we improve significantly on the CB and across the board. Okay, so that's basically our result. And zero shot, which means we have no data whatsoever in the target domain. And so we cannot really fine tune on the target domain at all. But we still manage to achieve better performance over all the transfer learning baselines. Okay. So we are in the era of large language models, and one common question I receive from a lot of people is that, what are some research problems that we still want to work on? Because we are already, ChatGPT already solves so many problems that previously people thought maybe still in progress or still unsolved problems. But with ChatGPT, these problems seems to have become trivial or solved. So what are some problems that we should be working on in the era of ChatGPT? So we are providing a new data set, which I believe poses a set of interesting challenges that even ChatGPT is not yet solving. Okay, so this one is known as, synopses of movie narratives. And those are basically consisting of watch a movie in 5-minute videos. Those are very popular on YouTube and a lot of social media. I'm sure you've seen some of these. And we have collected a bunch of these videos in total of more than 800 hours and more than 600,000 sentences. There are a bunch of reasons why this is a very good data set for story understanding, but I'm just gonna talk about a few things that I think will make the data set especially difficult. The most important reason is that the data utilizes storytelling techniques that may not be very easy to understand for a computer. For example, in this example, we see this headmistress Umbridge, right? It says Umbridge becomes the new headmistress. And in the video, what's really showing is that this woman is sitting in this chair that looks like to be a chair for the principal or headmistress or some powerful people, right? So the chair symbolizes a particular power status, but you have to pick that up Otherwise, you don't know why this video would, this text is a good description of this chunk of video. The second possible storytelling technique is to describe some causal predecessor or effects of the event depicted in the video. So in the video, we're seeing that is this woman shooting some person. We didn't see that person die, not in the video explicitly, but the text says, that this woman is able to kill this man. So what this is suggesting is that, you have to understand events that appear that are related to each other in a causal manner in order to match the video with the text. And the last one is that the data contains a lot of long-range dependencies, meaning events that are far apart relate to each other. For example, here we see a bunch of dwarfs hidden in those wine barrels, right? So, and the text says they arrange and escape using empty wine barrels. And in the second video that I think is about half a minute later, in this second video segment, we see that those barrels appear on the ship and the ship goes into the city. Now, the text says the company, the group of people, is smuggled into the city. So unless you can memorize and utilize the information that happens half a minute ago, which is a long time in video processing, you will not be able to match the video with the text, right? So you have to achieve that understanding. So because of these storytelling techniques, what we are seeing is that there seems to be some gap between the text and the video. So we estimated the gap. And our data set, I think there are some data set that has a huge amount of gap. There are some data set that has a little gap. I think this number is overestimated. The actual gap is way smaller than this. And our data set is kind of right in the middle. So I think this is kind of an appropriate amount of challenge for the next level of artificial intelligence. So we have designed the task to evaluate the amount of story understanding you have in the task. And we're trying to do matching of the video segment and the textual snippets. And as I was saying, unless you understand some of these storytelling techniques, it's not easy for you to align the video with the text. And you can see we have some state-of-the-art video text models such as UniVL and VideoClip, and they don't perform very well. And with our techniques, we have proposed some techniques and they work reasonably well, maybe a little better than what we had earlier with the models directly, but they're still, the performance generally is still pretty low. And I think there's a lot of room for improvement. And I think this will be an interesting benchmark about some really complex semantic artifacts like stories that will be useful in the era of gigantic large language models. So to sum up, we are witnessing the emergence of these large pre-trained language models such as ChatGPT or GPT-3 or a bunch of others from other labs and companies, and they are indeed transforming what we understand about AI and how we do AI research. These systems provide new capabilities, but also impose new challenges. And the research in my own lab have tried to utilize and exploit the new capabilities, such as language-based reasoning, and we also managed to solve some new challenges, such as few-shot prompt tuning to simplify the deployment of such models. Thirdly, we also proposed a new data set that still poses some challenge or to these large language models. So if you have any questions, please feel free to ask me right now or send me an email. My email is here. And with that, I'd like to conclude my talk and thank you for your attention.
For the sharing. If you have any questions, you can leave your comment in the chat box and I will read out for you and Doctor can answer you. You may leave your comments either from your Facebook account or your YouTube account. Okay, I saw a comment saying that they could not log into the Google form. I think if you have any issues regarding the Google form, you may leave an email to the email address we are going to add in the chat box. I think so far we have no questions, Doctor. Okay, sorry, we have one question. All right, a question from Miss Nisa Nazim. I have one question to ask. As you may know, cloud services such as load balancers and traffic routing, edge computing can greatly benefit AI models. From a cloud engineering perspective, will it possible in the future to deploy AI models of this scale in the cloud?
Okay, yeah. So thank you for the question. So it is possible to deploy such models in the cloud. Um, it's actually happening as we speak. You know, if you haven't played with ChatGPT or GPT-4, I strongly encourage you to do so and to experience the level of AI that we have at this moment. And that's what they're doing. So people are still speculating exactly how large is the model they're showing us online. Is it the full 135 billion parameters or 775 billion parameter model, or is it a much smaller model, which is easier to deploy? But it's really just a matter of cost. It's possible to host such models. It's just very expensive. And when you reach the popularity of ChatGPT, I believe there's servicing millions, if not billions, of requests every day. The cost is very high. So I think that's kind of the challenge. And uh, if you have a lot of requests, and if you don't have enough compute, if you don't have enough GPUs in your cloud, then you either respond really slowly, or you have to deny their service request from time to time, right? So you wouldn't be able to handle all the requests. Or alternatively, you have to buy a lot of GPUs and build a huge server room, and then you could do it, but it's very expensive. So I'm not suggesting that those are impossible to do, but rather we can lower the cost, we can simplify the deployment, and hopefully from an algorithmic perspective. But thanks for the question.
Okay, thank you for the question. Is there any questions? Any more questions from the crowd? If not, I think we could end our session today. So, um, all right. So no more question, doctor, for now. Sorry, one more question. One more question, doctor. Um, Dr. Albert, I'm concerned about data being fed to the AI without bias or filter, but want to know, is there a model that can allow the AI to understand this?
Right. So I think the question is about the training data and whether the training data contains certain bias that we don't necessarily want to see, right? If the training data could contain potentially offensive content or misinformation, or because the training data are crawled from the internet, which could contain a lot of incorrect knowledge, flat Earth. There are, of course, websites that claim that Earth is flat, and if you're not careful, that kind of goes into your training data, and you train the model on that. So I think this is definitely a problem that the designers of these large models at OpenAI are acutely aware, and they definitely try to reduce the bias in the training data. How exactly do they do that? They're not disclosing. So we don't have a lot of detail on training data. I think this is what their core competence is. The algorithm is open and it's relatively straightforward. The cleaning of the training data is where the secret sauce is, and they're not disclosing the secret sauce necessarily. So long story short, there are definitely a lot of research in identifying this misinformation or try to value data. If you have a particular test, can I estimate how valuable my data is, or each chunk of data is to the particular test benchmark? I have done some research in this regard as well, and I'm sure there's a lot of other people, a lot of researchers looking at these things at this moment. So this is a realistic concern. I don't think we solved this problem just yet, but I think we are working on it, and I think most researchers are aware of these challenge, and we're kind of looking at technical solutions. Thank you for the question.
Okay. Thank you, Doctor, for the answer. And I think there are no more questions. So I think we can wrap up this session. Before we end our session, I would like to thank all of you for participating in this public talk. And thank you so much, Doctor, for spending your time and to share with us your expertise in this topic. I think most of us have something to gain from this topic. And with that, I would like to close this session and hope to see you soon in near future, I guess.
Yes, thank you very much.
All right. Thank you very much, everyone.